Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. There is something very wrong with the Blue Engine 4, being built by Blue Origin. Blue Origin is a very secretive company, and they have not told us what the problem is, or let us see one blow up, like SpaceX would have. Let's see what we can figure out for ourselves. The place to start is back in time. The year is 2012, 10 years ago. In that year, SpaceX launched a Dragon capsule to the ISS, surprising quite a few in the space industry, and proving that while the main goal of SpaceX was to make humanity a multiplanetary species, it could still solve America's space needs on the side. Blue Origin was still working on its New Shepard suborbital tourist rocket, testing the solid rocket motor on their new crew capsule. But Blue Origin had another project going. In 2011, Blue Origin started to develop a concept for a large and powerful natural gas rocket engine. SpaceX decided to do the same thing with methane in 2012. Now let's fast forward to 2021. SpaceX had built and tested its 100th Raptor engine by July of 2021. In August of 2021, after more than 4 years of delays, Blue Origin announced that they had solved the technical issues with their engine and were assembling 2 flight engines. Why is there so much disparity between these two companies? Why is SpaceX perfecting its second-generation engine while Blue Origin is trying to get its first one off the ground? And in March of 2022, the lead rocket engineer at Blue Origin left the company after further delays of the New Glenn rocket, which is dependent on the BE-4, were announced. Correlation does not prove causation. 2 things happening at the same time doesn't mean one was necessarily related to the other. And the delays in New Glenn development were blamed partially on launch contracts going to SpaceX. But the launch contracts went to SpaceX because of the delays getting the BE-4 flight ready. ULA has lost several contracts and is far behind on development of the Vulcan rocket system, which is also dependent on the BE-4 engine. On March 22nd of 2022, ULA announced that they should have 2 engines by mid-year, and Blue Origin insists that these will be flight ready. What has taken so long? To make an educated guess, we'll need to take a close look at fuel choice and rocket engine development. The fuel chosen for the BE-4 is liquefied natural gas. Liquid natural gas is just unrefined methane with a small percentage of other hydrocarbons. Methane is the simplest possible hydrocarbon, having 1 carbon and 4 hydrogen atoms covalently bonded. Liquid natural gas is produced from the breakdown of organic matter buried underground. If you have heat and pressure for very long without oxygen, complex molecules will break down to simpler forms over time. 2 of these forms on their way to natural gas are coal and oil. Where you have coal or oil, you will have some natural gas. Over enough time, almost all the carbon-rich materials would break down, producing smaller and smaller hydrocarbons, until it was mostly methane. Bacteria on Earth and possibly Mars can also produce methane. These bacteria live where there is little to no oxygen, and break down organic matter or other chemicals into what we usually call swamp gas. This is mostly methane. All organic waste can be converted into methane and other biogas, including hydrogen. This can be done by organisms or chemical processes. While organisms turn complex molecules directly into methane, chemical breakdown is usually a step-by-step process. The next simplest hydrocarbon after methane is ethane, then propane, butane, pentane, hexane, heptane, and octane. You may recognize octane. This is the major hydrocarbon in the gasoline that we burn in our cars. The 87 you see on the pumps means the gasoline is about 87% octane. Most of the other 13% is heptane. We call this fuel gasoline because a gentleman in London named John Cassell advertised his patent gasoline oil, which burned bright and brilliant in lanterns, and was cleaner burning than the kerosene fuel that was commonly used in lanterns at the time. Kerosene produced a lot of soot. But this gasoline made a lot less. When a shopkeeper named Samuel Boyd started using the same name for a liquid fuel he was selling, he received a nasty letter telling him he could not use the trademark name gasoline. Mr. Boyd changed the C to a G and started selling gasoline. By 1863 in Britain, this was called gasoline and spelled this way. And the next year it started being sold in America with a slightly modified spelling. What made gasoline burn cleaner than kerosene? This is kerosene. This is what the Falcon 9, Soyuz, Delta III, Atlas, Antares, Astra, Rocket Lab Electron, and Firefly Alpha all burn. Kerosene refined and purified for rocket use is called RP1. Just like purified methane is more predictable but more expensive than natural gas, purified kerosene, with one known molecule, is more predictable but more expensive than plain kerosene. But RP1 still burns into many complex products of combustion. From kerosene, you could make lots of breakdown products, and it is very hard to get anything to burn perfectly. The fuel and oxidizer also need to be in the gaseous state for the molecules to mix properly and combust when they go into the combustion chamber. Turning into a gas is no problem for liquid oxygen, which has a boiling point of minus 183 Celsius. But kerosene has a boiling point of 150 to 250 Celsius, depending on multiple factors. That means before the RP1 rocket engine is burning, the heat is lower and not much of the RP1 is gas. This makes RP1 rockets harder to start. The boiling point of methane is minus 161.5 Celsius, much closer to that of liquid oxygen, allowing them to have a common dome. You will need two separate tanks, or insulation between RP1 and oxygen tanks, because the liquid oxygen is much colder. You will also need insulation on a downcomer that brings liquid oxygen through an RP1 fuel tank. Liquid hydrogen is much colder than liquid oxygen, so you need separate tanks or insulation to prevent the oxygen from heating your hydrogen in that case, and causing too much boil-off. Both methane and hydrogen gasify far below room temperature, making combustion of these gases in a rocket engine much easier. Let's look at why this is. It turns out that all of these hydrocarbons stick together, using van der Waals forces. While the hydrocarbons are themselves electrically neutral, when electrons are orbiting two or more atoms, the electron won't be everywhere at once. When its probability wave is distributed more on one side, that side will have a larger negative charge than the other side, which will have a higher positive charge. If two molecules are next to each other, these very small charges will cause them to briefly attract each other, causing these molecules to stick together like magnets. Since all of these molecules are passing in and out of these phases, van der Waals forces can hold them together. This is a very weak force, but the longer a hydrocarbon molecule is, the stronger this force becomes. If the molecule is very long, it will become a solid at room temperature and be called wax. As the molecule gets smaller, it will be liquid at room temperature, like gasoline and kerosene. And finally, if the molecule is short enough, it will be a gas at room temperature, like butane, propane, ethane, and methane. Natural gas was used in public lighting for a long time, and while it burns cleaner than gasoline or kerosene, a gas or cryogenic liquid would be hard to get into your car. So we use the liquids gasoline or kerosene in most of our transportation. There have even been gasoline-fueled rockets. These were built and tested by Robert Goddard himself, the father of American rocketry. But kerosene became more popular in German rocketry, which built the first functional liquid-fueled rocket. And kerosene is used for jet fuel, so it was easily available. Kerosene is denser than gasoline, giving more energy by volume. Remember that energy density is measured in energy per volume, joules per cubic meter, for example, while specific energy is measured in joules per kilogram. Specific in this context means by mass. Density measures a characteristic, like mass, by volume. So energy density measures the stored energy in a substance by volume. Mr. Goddard had stated long ago that while hydrogen had the highest specific energy, measured in joules per kilogram, of any rocket fuel, It also has a very low energy density, measured in joules per unit volume. This means that you need really big tanks if you use hydrogen fuel. Kerosene has a much higher energy density, allowing for smaller tanks. But with its lower specific energy, you don't get as much energy out of each kilogram. Mr. Goddard thought that methane would be a nice balance between these two. But methane was harder to get and use in his time. Let's look at another quality of kerosene. Kerosene, with its higher energy density, is both easier to store and easier to pump. A pump can hold a certain volume of liquid at any time. A centrifugal pump spins to move that liquid. The faster it spins, the more liquid it can move. If you had 3 pumps, all the same size, and spinning the same speed, you could move a lot more kilograms of kerosene than you could the less dense liquid methane or liquid hydrogen. You could spin the methane and hydrogen pumps faster, but pumps have limits to how fast they can spin. These limits have to do with the G-forces produced at the end of the blades. These forces can warp or crack blades, causing failures, like in this Antares rocket that exploded shortly after launch, when a turbopump failed and blew itself apart. This is a kerosene or RP-1 explosion. In order to pump the same amount of kilograms and not spin too fast, the turbopumps for methane would need to be larger, so they move a greater volume with each rotation. This is how big the turbopump was on the F1 RP-1 burning Saturn V engine. Compare the RP-1 pump to the liquid oxygen pump. Now this is the relative size of the Space Shuttle main engine pumps, burning liquid hydrogen and liquid oxygen. Hydrogen's low density is why this pump had to be so large. Here is the Raptor, showing the relative size of the methane and oxygen pumps. That's one reason why you can't just run methane through a Merlin engine. The engine would be fuel-starved because it was designed to move the more energy-dense RP-1. There is another issue with RP-1. Due to its higher boiling point, it doesn't turn into a gas and evaporate as easily, reducing explosion risk. But this high boiling point also makes it harder to turn into a gas and ignite, since liquid hydrocarbons can't burn until they turn into a gas. Gasoline and diesel engines will sometimes have a swirl chamber to heat and gasify the fuel before it is injected into the cylinder for combustion, to increase efficiency and improve ignition. Let's look at ignition briefly. For every combination of fuel and oxygen, there is a different temperature of ignition. While a tiny spark might ignite natural gas, it takes a lot of heat to start kerosene burning. If you put diesel fuel in your gasoline engine, it will quit working. This seems strange, since we said that kerosene has more energy per kilogram than gasoline. But kerosene doesn't gasify as easily as gasoline, and a liquid hydrocarbon can extinguish a flame or ignore a spark. The spark plugs in a gasoline engine do not generate enough heat to gasify and ignite diesel kerosene fuel, to cause ignition and create combustion. A diesel engine will use very high compression and glow plugs to get started. Remember that compressing something causes it to heat up. That is why a diesel engine does not have spark plugs. Once the glow plugs help start the engine and get the pistons moving, compression alone is used to heat the fuel and oxygen to combustion, causing it to auto-ignite once the engine is running. To get RP-1 to ignite and combust in a rocket engine, it needs to be started with a very high temperature. Most engines use chemicals that explode on contact with oxygen to light their RP-1 engines. There is more on how to light engines in this lesson. These chemicals are usually triethyl aluminum and triethyl borane, usually abbreviated TTEB. This burns green and is why you see a glow when they start an RP-1 engine. Here you see a Falcon 9, a Rocket Lab Electron, and a Firefly Alpha. The largest RP-1 rocket engine ever flown was the F1 engine by Rocketdyne. Let's look at the development of this engine for a minute. In 1955, the Rocketdyne Company was chosen to start working on a large rocket engine for the Air Force. The Air Force wanted a powerful engine for two-stage ICBMs. The first engine designed was called the E-1 engine. The E-1 was a large RP-1 burning gas generator engine. This engine was built and tested, but like all large engines, it had to contend with combustion instability. When a combustion chamber gets large, There may be areas that burn at different rates. This can cause explosion-like detonations and shockwaves that can damage your engine or blow it apart. While Rocketdyne was trying to solve this issue, Aerojet had designed and tested the LR-87. The LR-87 had two separate turbopumps and combustion chambers, really making it a dual-engine system, but it was considered as a unit, and the Air Force chose it over the E-1 for the Titan missile. The E-1 was shelved, but Wernher von Braun thought that a larger version, the F-1, could be a good choice for a moon rocket, if the combustion instabilities could be solved. The Soviets had the same problem trying to make large rocket engines, and they had the same solution as Aerojet: make multiple small combustion chambers and nozzles. The RD-170 has one turbopump and 4 combustion chambers and nozzles. The RD-180 is just 2 of these chambers with 1 turbopump. Because they have 1 turbopump, they are considered one engine. For the F-1 engine, Rocketdyne found it could put these dividers into the top of the combustion chamber and solve this problem. Other problems were solved also. When we burn some fuel in a gas generator to use in the turbopump, we usually keep it fuel rich, so as not to overheat the preburner and turbine. The exhaust from this preburner can then be fed into the nozzle partway down, to protect the nozzle with a cooler layer of gas. You can see this dark gas exiting here on an F-1. You can also pump fuel around the rocket nozzle to keep it cool. RP-1 can do this for a while, but heating and cooling RP-1 can produce long carbon chains that make plastic-like residue buildup. This is called polymerization. This is not really as much of a problem with methane-based engines. RP-1 also does not burn completely in a rocket engine and forms soot. This can start to block up the engine and is called coking. This is also not as much of an issue with methane and natural gas. But while the RP-1 burning F-1 was not reusable, the RP-1 burning SpaceX Merlin engine is. SpaceX must clean and refurbish the Merlin engines between launches. One of the ways these engines are cleaned is with high-pressure nitrogen gas. They had been cleaned with alcohol, but alcohol residue had caused an engine shutdown on one flight, and I don't think they use this anymore. The BE-4 will be using liquid natural gas, which, being mostly methane, burns much cleaner. So if methane is easier to ignite, burns cleaner, and gasifies easier, and the Raptor is already in its second generation, what is causing the BE-4 delay? I see 2 possible areas of difficulty. The BE-4 is a much larger engine than the Raptor. You can see here that the combustion chamber is much larger. It is very likely that early on the BE-4 suffered from combustion instability. If this was one of the problems, we would have to assume that the very smart people working on the BE-4 know about past solutions. Going to multiple combustion chambers would mean starting over completely. So whether they use dividers or some other solution, I don't think this would hold the engineers back long. Why doesn't the Raptor have this problem? Because SpaceX went a different route. The Raptor combustion chamber is much smaller than the BE-4's. And while the BE-4 is supposed to be more powerful than the Raptor 2, at 230 tons of thrust, is very close to the 240 tons that the Blue Engine 4 is supposed to produce. How is this possible? Let's look at what's the same and what's different on these engines. Both these engines are burning methane-based fuel. But while the BE-4 has a large combustion chamber, running at about 134 bar, the Raptor, despite its smaller combustion chamber volume, is running at more than twice that, 300 bar, and has been tested to 330. By using extreme pressure, you can make your engine more efficient. Just like the diesel car engine, compression improves combustion because it squeezes the reacting gas molecules together, making it easier for them to react. This reduces residence time. Residence time is how long the propellant must be in the combustion chamber to have time to react and combust. A shorter residence time means you can pump the propellant through at a much faster rate and still get near complete combustion. Why didn't everyone do this? Because you'll blow your combustion chamber apart. The highest combustion chamber pressure of any rocket engine before the Raptor was set by the RD-180 and stood for half a century. To accomplish this, the Soviets developed special alloys that could withstand the heat and pressure. SpaceX improved on these. While Blue Origin used an F1 type large lower pressure combustion chamber, SpaceX adopted the high chamber pressure approach. In fact, the chamber and nozzle mass, without turbopumps, of the BE-4 and the Raptor 2, as seen here, are 851 kilograms versus 852 kilograms. How can a much smaller combustion chamber with a slightly smaller bell nozzle have as much mass as a much larger one? This one must have a much thicker chamber wall, so it can withstand the ultra-high pressures. A smaller combustion chamber with very high pressure will have a lot less problem with combustion instability and a shorter residence time, allowing propellant to be pumped through faster, increasing thrust. And that brings us to the other possible issue. Both of these engines, of course, use turbopump systems. Nothing else can produce the power needed to pump propellant at these rates and pressures. Blue Origin adopted the RD-180 pump cycle, using a single oxygen-rich preburner and a single turbine. This is a staged combustion engine. This worked great for the smaller RD-180. The Raptor instead uses two preburners, one oxygen-rich for the oxygen side and one fuel-rich for the fuel side. This is called full-flow staged combustion. The Blue Origin turbopump uses just one oxygen-rich preburner to power this one massive pump that moves both the oxygen and the fuel into the combustion chamber. Now, single turbopumps can be this big. Here is one from the F1 again, but the F1 was pumping kerosene. A methane turbopump the same size would need to spin much faster. And the F1 preburner was fuel-rich, keeping it cool. The BE-4 is oxygen-rich. Increasing the power in the BE-4 preburner will create tremendous heat and oxidation stress on the turbine blades. Let's compare again to the Raptor. You can quickly see that this one pump must work much harder to move an adequate amount of propellant than these two pumps. To get high performance out of this large turbopump, the conditions here will be much more extreme than what the Raptor turbopumps experience. All preburners are small combustion chambers, with all the same pressure limitations and cooling problems. The Raptor pumps are being constantly bathed in cold methane and liquid oxygen, allowing them to run at a lower temperature. The BE-4 turbine is not. Overheated metal breaks down much more quickly than properly cooled metal. And since there are two pumps in the Raptor working together, they don't have to work as hard as the one Blue Origin pump. I think it is most likely that combustion instabilities were a problem for Blue Origin early in BE-4 development, but were most likely solved fairly quickly. And that it is very possible that the problem Blue Origin is having trouble solving now is getting enough heat and pressure into this oxygen-rich preburner to power this massive turbopump system without blowing it apart or damaging the turbine blades. I don't think the turbopump is holding together well, though they may be able to get it to work for a single flight, possibly saving the Vulcan rocket, which is not reusable. I don't think they will easily be able to reuse the BE-4 with this design. And the BE-4 is supposed to be a reusable rocket engine. It is supposed to power the New Glenn through multiple launches and landings. But for a rocket engine to be reusable, you don't want to overstress any components. That is why the Archimedes engine, being designed by Rocket Lab, will not have any extreme performance parameters. Blue Origin, on the other hand, may have discovered that scaling up the RD-180 preburner and having this giant turbopump run under extreme conditions was a bad idea. We would like to know what you think. Please don't forget to like and subscribe, and we appreciate your help on Patreon. Stay safe, and thanks for listening. At Astra Pro Terra.